Hello everyone, welcome to physics. Now today we are going to be talking about one-dimensional kinematics, and this is going to be part 5 of this chapter, and today is going to be the last part. The rough idea of today's presentation is that we'll be recapping everything that we've done so far, and we will be discussing free fall today, or I'll be going over free fall, and particularly I'll be trying to demonstrate how the equations of motion can be applied to free fall in one dimension rather than two dimensions, or rather than studying projectile motion, which is going to be next as in a chapter or two. But without further ado, let's start with just a recap of what we've done so far. And that includes that we've gone through distance, displacement, frames of reference, which includes both reading the position and how to extrapolate data out of it, which includes stuff like the position from the original from the measuring location or the point of reference, right? Using Pythagoras theorem. Then we went through speed, velocity, acceleration, and based on from distance all the way to acceleration, we discussed what's a scalar quantity and what's a vector quantity and what is the difference between the two. The next part that we did was to do the reading from the position time plots and the velocity time plots, which was what other sets of data that you can get out of it. The next part that we did was, this is just a recap of what the distance was. So the distance is the difference between the positions of 2 points, right? The displacement, on the other hand, it's the difference between the space, or the shortest difference between 2 points, right? And then you have a direction associated with it. Speed is simply distance divided by time. So it's a scalar quantity, same as distance. It has a magnitude only and it has no direction. Velocity, on the other hand, is the displacement divided by time, right? And it has, as is the case with displacement, it has both a direction and magnitude. And then finally, acceleration is the change, or the net change in velocity divided by the net change in time. And again, acceleration, because it's a vector quantity being divided by a scalar quantity, it is a vector quantity, i.e. that it has both a magnitude and a direction. As you could recall from yesterday's lecture, that gravitational acceleration or acceleration due to gravity is acting downwards, and it's attracting you towards the center of the earth. That's where the direction is. Now, the other part that we went over was were the equations of motion. The first equation was that we had a relation between the final velocity based on the initial velocity, the acceleration, and the change in or the net change in time. The second one included the change in displacement, which was a function of the initial velocity, the net change in time, the acceleration, and the net change in time squared. And then finally, the third one was the square of the final velocity, is a function of the initial velocity squared, the acceleration, and the total net change in displacement, or the total change in displacement. These are the three relations that we derived. We derived these two relations, and the third one was something that you had to derive. And these are the ones that I kind of showed you how we started from a basic position time graph, and we worked all our way through to get to this little equation using the basic relations that I'd shown you in the slide just before this. Now, the next part that we were going to cover today, we were going to go over these free fall examples, where I had asked you to, essentially try to find that how what would be the velocity if you were to drop a ball from a 10-meter high building, and what would happen if you were to throw the same ball upwards with a velocity of 15 meters per second. And what you had to find out was what happens if you throw it at 15 meters per second upwards and then it comes back downwards. What is the velocity going to be when it reaches the rooftop level? And then what is the velocity going to be when it is just before impact on the ground? And then the last question was, what is going to be the answer to problem one, which is just dropping the ball from a 10-meter building if you were on the moon, where the gravity is now 1.6 meters per second square. So now the presentation will cut off to a video of me working on the Jamboard. I'm just going through these problems. So there are multiple ways for you to solve this. Let's start by drawing what the problem is, what the problem question is, because visualization of what the problem is trying to ask you, that helps with this situation. So let's say that this is our building right here, and this is equal to 10 meters, right? This is our person standing right here, and this is the ball, which is, let's assume that it's at level with the rooftop, right? So at time t is equal to 0 seconds, right, the ball is at an initial speed of 0 seconds. Anytime greater than that, or greater than, so at t greater than 0 seconds, the person lets go of the ball, right? So vi is going to be greater than 0 meters per second. This should be meters. So that's one thing, and you need to find out what the final velocity is going to be just before impact. So what VF is going to be in meters per second. So one thing we can do is we can start doing this graphically, or just by in a stepwise method. So I can say, let's say that my at t is equal to 0, vi is equal to 0. At t is equal to, let's say, 0.1 second, what is vf going to be, right? So we know at this point that our original equation of motion that we derived, the first one, the very first one that we did, is given by vf is equal to vi plus at, right? Now, the important part is a. Most of you were confused based on the questions yesterday. What is a? If you go back and watch all the videos, in one or two of the videos, I've mentioned that gravity, also known as acceleration due to gravity or gravitational acceleration, again, is a form of acceleration. If you look through that slide again, the units were meter per second square. If you go back to your dimensional analysis, we had mentioned, or you'd find out that the units for acceleration were meters per second square. If you go back to, I believe, Friday's lecture, you would also notice that a is, or acceleration is a function of, or is given as the net change in velocity over the net change in time, right? And if you were to do a dimensional analysis on this, this is going to be meters per second divided by seconds, right? Which, if you were to work it out around here, this is going to be meter per second times 1 by second is going to be meter per second square, right? So this is your dimensional analysis. So gravity is a form of acceleration. So what I was talking about earlier is that you can say that, let's say t is equal to 0.1 seconds. What is v going to be at this, or vf is going to be, what is going to be vf at this point? So you can plug your numbers into this equation. Vf is equal to vi plus at. Vf is something we are looking for. Vi was 0 plus 9.81, because, again, if this is our building, this is the ball that's being dropped. It's moving vertically downwards. Our gravity is also acting downwards. So all those things are pointing into the same direction. So you can say that that direction is the same. That's why we're using all positive signs. And then you've got 0 plus 9.81 times zero point 0.1, which is equal to 0.981 meters per second. The next step then would be to increase the time. Let's say that I do t is now tf is zero point 0.5 seconds. So where is the ball going to be? So this is at 0 seconds. This is at zero point 0.1 seconds with a velocity of 0.981 meter per second. Where is the ball going to be at zero point 0.5 seconds? So I can do that. That my tf is zero point 0.5, my ti is 0.1 second. My VI was, in this case, 0.981 meter per second, and my VF is something that I still need to find out. And A is going to be 9.81 meters per second square as before, acting positive uh, downwards, right? So what I can do then is plug it back into that equation, the original equation that we talked about. So let's rewrite that equation that Vf is equal to Vi plus At, which then becomes Vf is equal to 0.981 plus 9.81 times zero point 0.5 minus zero point 0.1, which moving on to the next frame is going to be Vf is equal to 0.981 plus 9.81 times zero point 0.4. This becomes 0.981 plus 3.924, which is then equal to 4.905 meter per second. Right? Now, how do we know how much distance has been covered? So if you go back to your distance or displacement equation, because they're essentially the same, or sorry, the velocity equation, where velocity is basically delta x by delta t. Now, we know what our delta v is in this case because we know what vf is, right? We know what this vf is, and we know what vi is. So I can rearrange this equation, write it down here, which is that delta x is equal to delta v times delta t, right? Um, and that would make it so my delta v in this case is 4.905 meters per second, and my time is zero point 0.5 seconds based on our original starting point where both the velocity and the time were at 0 meters per second and 0 seconds respectively. And this turns out to be, let me just pull up my calculator, times zero point 0.5, and this is equal to 2.45 meters, right? And remember, our original building is standing at 10 meters, so we're about quarter of the way through before we're reaching the ground. So that's one way for you to solve it. You can keep on working with the time, and you'll see that eventually you'll get to this point. What is the other method that you can potentially use? Let's go back to our original equations that we derived earlier. So we have one equation that says Vf is equal to Vi plus At, right? That's our one equation. Our second equation is that delta x is given as Vi delta t plus half a delta t squared. And then our third equation was Vf squared is equal to Vi squared plus 2a delta x. Now let's have a look at these equations more carefully, or let's have a look at our original problem where we have this is our building, this is our ground level, and this measures 10 meters, right? And the ball is being dropped up from here. So what we know so far is if this is our ball, Vi is equal to 0 meters per second. Ti is equal to 0 seconds. Tf is unknown. Vf is unknown. Delta x is 10 meters. And A is 9.81 meters per second square, acting downwards, positively downwards. So based on all of these right here, all of these values right here, and looking at these equations right here, um, which one of the equations will fit the best? So let's look at the first equation. We don't know what Vf is. We do know what Vi is. We do know what A is, but we don't know what delta T is. Similarly, if you look at the second equation, we know what delta X is. We know what Vi is, but we don't know what delta T is, right? So we've got one unknown here, one big unknown here, right? And we're looking for Vf. So, or the question is asking for Vf. So if you look at this third equation, we have our unknown. That's the one that we're trying to look for. So we want to find out what Vf is. So that's one thing that we don't know. We know what Vi is, we know what A is, and we know what delta X is, right? So you can use essentially these two equations, whichever one that you want to work with. The second equation, if you use this one, you'll first find what delta t is, and then you can substitute delta t back here and work out Vf is. The shorter method is that you use this equation, which we're going to do, and what you're going to get is, so substituting these values into the third equation right here, Vi is equal to 0 square, 0 meter per second square, plus 2 times 9.81 meter per second square times 10 meters, right? And that's Vf squared, which then, if you were to work out or calculate, becomes, let's see, let me pull out my calculator, and this becomes 2 times 9.81 times 10 is equal to 196.2 meters, and meter multiplies, so meter squared per second square. And if you were to square root that, 196.2 meters squared per second square, what you will get is 14.007 meters per second, or nearly 14.101 meter per second. So question two was a two-part question, and then question two, part one, essentially it was had a little trick to it, where it's now telling you that the ball is thrown upwards, right, at a velocity of 15 meters per second, and then it returns back to its original location, and it wants you to find out what this final velocity is going to be, right? So the trick to this is in terms of direction and in terms of what the flight path is going to be. So you know the ball is going to first go upwards and then it's going to fall back downwards following the same path, right? And what the velocity is going to be. We also know that the velocity here at launch point was 15 meters per second. The trick is to find out what the velocity is going to be here when it reaches the top. Now, consider this. When you throw a ball upwards, what is happening? The ball is essentially slowing down. Why is it slowing down? Because it's being acted by gravitational acceleration, which is slowing the ball down, disregarding air drag at this point, right? So gravity, which is acting at 9.81 meters per second square, is slowing the ball down because the ball is now trying to move up, right? So in this case, you have to take care of your directions as well, right? So that's one thing that you have to look into. So what happens when the direction changes? What happens at this point right here? At this point, as the ball is moving up, when it changes direction or when it reaches its the most height, what happens is that v here, or v final in this case, is going to be 0 meters per second, because the ball has essentially seized its motion when it reaches its highest point, and then it starts to fall back down because it's being acted by gravity. So let's start with this. Let's say this is the ball at the rooftop level. And since gravity is acting downwards, and gravity is taken as positive downwards at 9.81 meters per second square, and ball is launched upwards, let's start with this. You've got a negative 15 meter per second velocity, right? So here our frame of reference is positive downwards from our original location. Right, and what we know is that this is our VI, and VF in this case is going to be 0 meters per second. Now, going back to the original equations right here, what we know now is our acceleration term. We know what VI is, and we know what VF is. What we don't know is what delta x is going to be. So coming back to this page, we are using that same equation, that VF square is equal to VI square plus 2a delta x. I can rearrange this equation to write that VF square minus VI square over 2a equals to delta x. And just substituting in the values, you will get, right, so plus 0 squared minus, this is a square right here as well, minus 15 squared over 2 times 9.81. This is going to be equal to negative 225 divided by 2 times 9.81 is going to be 18, and then 1.62, so 19.62, I believe. And what you're going to come out with is then that this is equal to negative 11.48 meters. So the ball is going to travel upwards by negative 11.48 meters. Now, why is there this negative sign? That is a very valid question. Now, remember when I said that you're starting at this little point right here, and this is our origin, and everything downwards is being measured as positive, and everything upwards is being measured as negative. Because you're traveling upwards, your original your displacement for this leg of the journey is going to be negative, right? That's why you end up with negative 11.48 meters. If you had considered the other way around, that your upwards is positive and your downwards was negative, and so gravity was negative, your value would have come out to be positive, and that's fine, because and that's where frames of reference and direction and magnitude come in into vector quantities. So that's one part of the question that you've solved. The next part is the return leg of the journey. So what we know so far is that the ball has traveled upwards for 11.48 meters, right? Where it became static, and now it's going to fall down, right? So it's going to fall down 11.48 meters, or it's going to cover a distance of 11.48 meters before it reaches the rooftop level. And then it's going to cover another 10-meter distance before it hits the ground. And what we need to know is, what is the velocity going to be at this location for part one, what VF is going to be, and what VF is going to be when it reaches this 10-meter mark. So what you can do is, again, using the equation, the third equation of motion, that VF is equal to, or VF squared is equal to VI squared plus 2A delta X. Now for the rooftop case, remember now everything is pointing downwards. You can now define a new frame of reference here, and everything is positive downwards. So VF is going to be, for the rooftop level, 0 squared plus 2 9.81 times 11.48, right? Because you're traveling downwards, square root of the answer. So this equals 2 times 9.81 times 11.48, and square root this answer, and you're going to get 15.01 meters per second. So using the same equation to find out what the velocity is going to be before impact, at the ground level for part B, we have Vf is equal to, we've got a square root, Vi is 0 meters per second squared plus 2 times 9.81 meter per second squared times delta x, which is in this case going to be 11.48 plus 10. So starting off our journey right here, 11.48 plus 10, 21.48 meters. And if we were to do the same calculation again, it's going to be, you should get 20.53 meters per second. So that's how you were supposed to solve this part. Now, there are quite a few more things that you can also extract from this data, and that's essentially that you can find out what the time is. And since we know what our VF is, we know what our VI is, we know what A is. For each of these questions, you can find what delta T is using basically equation 1, which was VF is equal to VI plus AT. Even without finding VF, if you were to use the second equation, you could find out what delta T is by just substituting the numbers in there, which was VI delta T plus half A delta T squared, right? So you could have found out everything from there as well. Now, the third question is asking you what would happen if you were to drop the ball from the same building, but you, instead of being on Earth, you were on the moon. So you're, for problem 1 at least, now in this case, your gravity has now changed from 9.81 meters per second square to 1.6 meters per second square. So using the same equation, Vf squared is equal to Vi squared plus 2A delta x, and then rearrange it to find, oh well, that's already arranged that way. Vf is equal to Vi squared plus 2A delta x. Again, the building, or this height before it reaches the ground level, is 10 meters. So you've got 0 squared plus 2 into 1.6 into 10 square root, and that should give you an answer of 5.66 meters per second. I hope this clarifies things. So we've covered both all the 3 questions, including the 2 parts of question number 2. Now, if there are any questions, please let me know after this. After we go back to our original presentation or the slideshow, there are a couple of videos for you to watch. So returning to our original presentation. So the next part, I would like you to visit this video first if you've got questions. Of freefall, there are a couple of experiments that are in here, which you'll find really interesting. The link is going to be attached in the presentation file that is going to be posted on your classroom. And then the second one is to do with a bowling ball and a bunch of feathers being dropped in a room with normal atmospheric pressure and air. And the other one where the pressure is nearly 0 because all the air is being extracted and you're sitting in vacuum. And the results are quite interesting. So that's one thing you have to find out. And with that being said, that's the end of the lecture. Please let me know if there are any questions. This also wraps up our chapter or unit 1, which is one-dimensional kinematics. There's going to be a homework assignment that will be attached with this notification, or with a new notification that will be due in a week's time. Please go over this course content. The videos are distributed over 5 parts, and please let me know if there's something that I can re-go over and clarify things. The Derivation, I will look through the derivation parts. If they're not clear, based on the answers that you've given me, I'll make another video. I'm not so sure about that yet, but you will find out soon enough. And with that being said, enjoy the rest of your day. Please remember to turn in the class activity which is going to be posted by 5 p.m. That's to do with your attendance. And other than that, thank you for your attention, and bye-bye.